Hello everyone, we are going to present our project on superpixels in pairwise CRF for segmentation. My name is Ankur.
I'm Eni.
I'm Rohit.
I'm Yash.
Okay. So semantic segmentation is a fundamental problem in computer vision. It has applications ranging from autonomous driving to medical imaging to satellite imagery to pose estimation and just general object understanding. The hard part about semantic segmentation as compared to object detection or classification is that every pixel has to be correctly labeled, which makes it a fundamentally harder problem, but it also means that if we can do it successfully, we can have wide strain applications to downstream tasks. So recently, a lot of deep learning architectures have been used to approach this problem. FCNs are fully convolutional networks, were first used by Long et al. In 2015, and they use CNNs, but they produce coarse outputs. So oftentimes people have recently tried to use CRFs as post-processing. So using a fully connected CRF, we can perform either variational inference or approximate inference with a RNN. But the problem with these is that a fully connected CRF is overkill. We think that we suspect that we can perform inference without a fully connected CRF and make inference less expensive. And also, in order to do this in practice, we use a mean field approximation, which often doesn't perform very well. And if we instead use a constant like patchwise distribution, then we might not capture semantic dependencies very well between different objects.
Okay, coming to the method. So instead of using a fully connected CRF at pixel level, we propose to use superpixels as nodes in our conditional random field. So if we use superpixels, then inference is much easier, and because we have lesser number of nodes and edges, and we also don't have to use it as an end-to-end training model. We can use it as a plug-and-play model for post-processing the output of any other model, for example, FCN. And here is the slick algorithm which we used for extracting the superpixels. And here are some segmentation results from Slick. So in most of the cases, the boundaries of the ground truth aligns with the boundaries of the superpixels. And conditional random field is nothing but a Markov random field which is conditioned on some input. In our case, that input is the image. And so the Gibbs energy has two terms. One term comes from the unaries, and the second term comes from the pairwise potentials or the edges. And once we have the Gibbs energy, we can write down the probability distribution of the labels given the input image.
To figure out whether using superpixels to segment images can actually work, we first construct a diagnostic upper bound, which upper bounds all possible performance that we could possibly achieve using any sort of CRF. So to do this, we first use Slick to generate superpixels. Then we get the ground truth labels for all of the individual pixels. Now, at each superpixel, we assign that superpixel the label corresponding to the most frequent label amongst its pixels. Doing this, we can find out what the best possible performance from any possible post-processing technique using superpixels will be. Our unary potentials for our CRF are supplied from a fully convolutional network, which is a unit in our case. Our first architecture that we test out is one without any pairwise terms. It has only unary potentials. The unary potentials again are supplied through the FCN. We use Slick to segment some superpixels from the input. We combine the two by taking an argmax over the predicted labels at each superpixel to construct our final prediction. This is an absolute baseline, and all of our further experiments with pairwise terms should aim to beat this baseline. We're going to consider three different types of pairwise potentials: the Potts model, the color Potts model, and the Gaussian edge potentials. In the Potts model, the pairwise potentials are simply an indicator function of whether the labels of the two adjacent superpixels match or not. In the color Potts model, this indicator function is multiplied by the boundary length, and it is divided by the boundary length between the two superpixels, and it is divided by the distance between the centers of the two superpixels. So superpixels that share a longer boundary should contribute to each other's potential functions more, and superpixels that are further away from each other should contribute to each other's pairwise terms less. In the Gaussian edge potential case, the indicator function is scaled by a Gaussian, which measures similarity in both the color space and also in the coordinate space. To perform inference on our CRF, we use Gibbs sampling so that we have a zero bias approximation. We However, Gibbs sampling is usually very ineffective because it requires OFN updates. It requires OFN time complexity to update all of the nodes. In order to make this faster, we take advantage of the fact that we can update multiple nodes simultaneously. We do this with the help of graph coloring. All of the nodes with the same color can be updated simultaneously by doing blocked Gibbs sampling, and it only takes the total number of colors, number of iterations to update all of our nodes. We've implemented block Gibbs sampling in Python with Numba for an extremely fast and real-time inference on the graphical model.
So let's talk about the problems related to pairwise potentials. So you need to observe that in all these pairwise potentials that Ankur and Yash discussed, uh, the the energy for same labels is always zero because the indicator function is zero, and the energy for any dissimilarity in labels is a positive value. This is not really an accurate model, as we see next. So for example, consider two nearby superpixels, one of which is green and one of which is blue. In that case, it makes more sense for the potential for grass sky to be more than grass grass or sky sky. But in this case, we will have that grass grass or sky sky being the same labels have better chance of being accepted. So this pairwise potential does not provide flexibility, and it is better to learn these pairwise potential directly from data. So coming back to the CRF's objective, we need to maximize the log probability of label given image, which is basically this. And if you take gradients with respect to, can you go back? If you take gradients with respect to parameters theta, you get a difference of two gradients. So the first gradient is a expectation over data, and the second gradient is an expectation over the current CRF. So let's discuss what they mean. So the first term is basically the gradients of the energy with respect to the data, and the second one is with respect to the data, is with respect to the current CRF. What this means is that we want to maximize the energy of the labelings present in the data and minimize the energy of all other labelings that might arise from the CRF. And this way, we are maximizing the probability of these labelings occurring. And we use contrastive divergence to sample from the current CRF. To test that whether these pairwise potentials are learned effectively, we construct a donor dataset consisting of various binary rings, as you can see, with various input and output radius, inner and outer radiuses, radii. We compare our performance with the Potts model. So Potts model has this smoothness assumption, which leads it to close these gaps inside the rings, as you can see in the second image. And in the first image, there are some random perturbations to the ring. Since our model learns the unaries and pairwise potentials separately, it has more robust outputs, as you can see. So in the last and first image, you can see that the Potts model has some arbitrary protrusions in and out of the ring, and the gaps are all closed. But in our case, the gaps are open and the surfaces are much smoother.
So coming to the experimental results, we show our results mainly on the epithelium segmentation dataset, and we also have some preliminary results on the Pascal BOC dataset. So we run grid search on all the parameters to find the optimum parameters for our model. In case of color pots, we have a total of 45 configurations, and and for Gaussian edge potential, we have a total of 960 configurations. Here are our final results. So the diagnostic upper bound is quite high. So it says that we can get up to a die score of 0.97. And with using just the FCN without any post-processing, we get 0.76 die score. However, in for all of our post-processing models, which are hand-coded, none of them can beat even just the FCN. So if we look at the Gaussian edge potential or the color pods, they reach up to 0.75, which is still lesser than what the FCN itself gives. And as for the learned pairwise potentials, our network still hasn't converged, so maybe we can put the results in the final report.
So here is a summary of contributions. So first of all, we perform a comprehensive study of the hard-coded potentials that are used in the segmentation literature. Next, we justify Gibbs sampling as a zero bias alternative to variational inference-based methods. And we implement a module for fast and efficient block Gibbs sampling. And this block Gibbs sampling is done using K coloring of the graph nodes. And finally, we propose an arbitrary learned pairwise potential term. And we show its results on a proof of concept toy data set. That's all. Thank you.